Hello, good morning. I'm Hiba Jababria. I'm a PhD student on the University of Tours, France. It's my pleasure to be here. So today I'll be walking you through my work on integrating LLMs in service-oriented architectures for personalized healthcare activity recommendation. My work was accepted on the International Workshop of Artificial Intelligence on Healthcare Informatics of the International Conference of Web Intelligence and Intelligent Agent Technology. So to guide us through this, my presentation is structured in four main parts, as you can see. First, I'll set the stage by outlining the context and the key challenges that lead us to formulate research questions to motivate my work. And then I'll dive into the proposed solution and its core components and the relationship between those components to answer the research questions. Then, after that, I'll show you some of the experimental results we've obtained. And finally, I'll wrap up with perspectives and the ongoing work. So let's start with the why. In oncology and in the medical field generally, the focus is often on treatments and medications. But what happens beyond that? We know that a patient's journey involves much more than medication and treatment, of course. So first, for example, we have the supportive care, like adapted physical activities, nutritional support, and mental well-being, like therapy, meditation, yoga exercises, and so on. So these factors are crucial for improving quality of life of the patient. Our vision here is a holistic approach to that seamlessly blends conventional medicine with these essential supportive elements, all centered around the patient's unique profile and pathology. This vision, however, is easier said than done. In practice, we face several significant hurdles and challenges. So first, the patient information is often scattered across different systems, so making it hard to get a complete picture. The first challenge is bringing together all this medical information to form one picture. There is another major challenge, which is the personalization gap. So what works for one patient doesn't for another, obviously, and it's difficult to ensure recommendations are both doctor-checked, clinically safe, and at once tailored to the individual case. Another challenge is patients are struggling to find and access appropriate services. It means after the recommendation, the patient needs to know when, where, and how he can practice and apply those recommendations. And perhaps the biggest challenge is the dynamic adaptation, since a patient's condition is dynamic, but our systems are often static. So our central question here became, how can we bridge these gaps in a systemic way? This question led us to formulate two core research questions that guided our work on that paper. So just to inform that we have more than two research questions in my project, but the scope of this paper is to answer these two research questions. So the first research question is, what kind of architecture do we need to build that can handle all this heterogeneous data and generate scalable recommendations that adapt as the patient state changes? The second research question is, how can we actually evaluate these recommendations to ensure they are both clinically safe and personally relevant to the patient? We need to balance this trade-off. To answer this question, and especially starting with the first research question, talking about the architecture, we designed this integrated framework in the form of a pipeline. So let me walk you through this framework. On the top, as you can see, our multiple data sources. So we have the medical guidelines, regional activity databases, and patient profiles. These are integrated via service-oriented architectures using the APIs, which provides the flexibility and interoperability we need. This data After that, fuels a retrieval augmented generation pipeline, which I'll detail in a moment in the next slides. So the RAG output helps the LLM recommender generate candidate suggestions, of course. And finally, these personalized recommendations are delivered through a mobile application used by patients, coaches, and doctors, closing the feedback loop. So, as you can see, the core of our recommendation workflow uses the RAG pipeline, a patient query which is fixed. These two are combined in a prompt that will be the input of the LLM recommender. So let's zoom in on the first part, which is the multi-source data integration. The power of my system comes from its ability to synthesize different types of data. We integrate dynamic patient profiles, which include things like their current activity level and treatment status, age, cancer type, and so on, with heterogeneous data from structured sources like the medical knowledge guidelines and the regional activity registries. But raw data, as you know, isn't enough, especially in the context of medical healthcare. So it needs to be structured in a way that machines can understand and reason with. So we have the medical, first we have the medical guidelines and the medical reference. This, it's a source document, begins with a PDF document containing evidence-based recommendations for supportive care and physical activity in oncology. So this medical knowledge is first manually extracted to ensure accuracy. This information is then refined by removing secondary content and systematically structured into nodes and relationships, forming the foundation of a knowledge graph. So this enables semantic enrichment and standardized information representation. We have, on the other hand, patient profiles. So this component manages dynamic patient profiles that consolidate essential clinical information, including age, cancer type, current treatment stage, and so on. These profiles are systematically integrated to form a standardized and comprehensive representation of each patient state. So we update these profiles continuously to serve as the fundamental data layer for generating personalized recommendations. And finally, we have the regional activity registry, an external registry containing descriptions of physical activities in the region. So it's pre-processed to remove noise and irrelevant data, of course. The information including names of public entities, accessibility, time, contact, pathological relevance, and so on. So we have this structured knowledge now. The next challenge is to ensure that our AI uses it reliably. This is where the RAG comes in. So the RAG, or the retrieval augmented generation, prevents the LLM from hallucinating by grounding its responses and generated activities in verified sources. So the process has 4 key steps. We ingest first the data via service-oriented architecture APIs. Then we split the documents into smaller coherent chunks. Each chunk is converted into a vector embedding. It means a numerical representation that captures its semantic meaning. Then these factors are stored in a specialized database. When a patient query comes, we perform a semantic search to retrieve the most relevant chunks, which are then fed to the LLM, and this ensures the recommendation is context-aware and evidence-based. Now that we have the right context, we do generate the recommendations. But the question here is, how do we generate and choose the best recommendations? So first, we construct a prompt that combines the patient's profile with the retrieved knowledge. This ensures consistency. So the LLM then generates a set of candidate recommendations, but not all these candidates are equal in the accuracy and the utility. So then we evaluate each one using a utility function. As you can see now, the MCS. So the function MCS combines 2 key scores. We have F1 and F2. The first subfunction, F1, measures how well the recommendation, this candidate recommendation, fits the patient's personal context. And the second subfunction, F2, measures its alignment with the clinical guidelines. The weights epsilon1 and epsilon2 allows us to balance personalization and safety, and this will be validated by a medical expert. Let me briefly break down how we calculate these two scores. So for the F1, personalization score, it's the cost and similarity between the embedding of the patient's profile and the embedding of the candidate recommendation. In simple terms, it measures, does this recommendation sound like it is for this specific patient or not? And the F2, the clinical alignment score, it's the maximum similarity between the recommendation and the database of clinical guidelines. So it answers the question, is this recommendation medically sound and safe for this patient? So a great recommendation, of course, is useless if it doesn't reach the user effectively. So we designed a multi-user interface as this last and the third and the last module of our pipeline. So for patients, it's about receiving those personalized activity plans, providing real-time feedback on how they are feeling and communicating directly with their coach and doctors. For experts, like coaches, it's a dashboard to monitor their assigned patients, adjust the recommendations if needed, and maintain that vital human connection between patients and experts. To test our system, we used a set of diverse patient profiles. So since getting those data of the patient profiles was a bit challenging, so I generated those profiles artificially using a Python script. So as you can see, we simulated the patients with different ages, cancer types, and activity levels, from a young athletic breast cancer patient to an older with a lung cancer patient. So this diversity was crucial for testing the system's adaptability when the patient state changes. So what were the results? We evaluated our system using the utility function with different weight configurations. So you can see here for patient 1, for example, when we prioritized personalization with a higher epsilon1, we achieved the best utility score. This trend was consistent across most patients, as you can see from patient 1 to 5. We get better result when we privilege the personalization. And the key takeaway here is that our personalization-focused approach consistently gets high utility scores, successfully balancing patient relevance with clinical alignment. We get all results bigger than 80% accuracy. So to choose the best balance, we need somehow a medical expert validation to choose which the case is more balanced, if we privilege the personalization or the clinical safety. Looking ahead, our work now is far from over, of course, so we have several exciting directions. Our top priority now is real-world deployment and evaluation, using more data, using real patient profiles to test and validate our results in clinical settings. We are also working on enriching our medical knowledge base, the medical guidelines, by integrating the SNOMED city ontology for even better semantic reasoning. And crucially, we are focusing on reinforcing data privacy later through techniques like federated learning, using local LLMs, blockchain, and so on, to ensure we meet standards like GDPR and the HIPAA. That brings me to the end of my presentation. Thank you for your attention and interest, and I hope my work gave a significant contribution in the scientific community.